Hi everyone, I'm Sasha. I highlighted my name on the slide. I'm going to talk to you about a project that I worked on at Lincoln Laboratory with the co-authors maybe 5 years ago that never went anywhere. So it's a little bit rusty, and it's just a neat idea that we were sorry we couldn't ever prove anything with. Had some computer issues today. My computer doesn't really want to charge, and I had a crash on Keynote. So at some point in the slides, I'm going to have to switch over to showing you the images from our actual document and get out of the slides. But luckily, we have beautiful images in our actual document, so it should be fine.
It's okay, it's on brand.
Yeah. Okay, so first of all, what's multi-party computation? A lot of people in this room already know, but general idea, you've got a bunch of parties. They want to securely compute some functionality F together. Some of them have inputs to that function, maybe all of them do. Maybe the functionality is voting or something and everyone wants to put in their vote. But some of them do. And the functionality is going to give them some output back to all of them. Multi-party computation says, what if you don't want to have some trusted party to do that functionality for you? Can you define a protocol that will do it instead? And you want this protocol to be secure and correct. Okay, so the other part of my title is communication locality. What does that mean in the context of multi-party computation? So the idea is, what if you don't have like 6 parties, like on my first slide, but you have a ton of parties. You have a bunch of computers working together, some really big number, like N. If they're all talking to each other, the communication graph is absurd. It took me a long time to write that communication graph. And what we would like is to have a better communication graph. We want each party to not have to talk to that many other parties. So, maybe it looks like that instead. Okay. Okay, so that's our goal, is to try to lower communication locality. Formally, which I didn't write in the slide, it's, if in the communication graph of the protocol, the highest degree that any one party has is the communication locality. So the question is, how low can you go with that communication locality? This is a question that in different forms has been looked at for a really long time. I put a few of very many citations up on this slide. So, Byzantine agreement's been studied for a very long time, and if you have an adversary in your multi-party computation protocol who can just decide not to send messages, then it's fairly easy for that adversary to just isolate people. And so that they can never get the output of what even if you're just trying to get everyone to agree on a value, you can stop people from ever seeing that value by just surrounding honest parties with adversarial parties who sort of cut them off. So this has been established since the 80s. If you have T corruptions, then you need that, any cut in the graph has to have at least T+1 edges. Okay. One way around this, which is something that people have been looking at more recently, is if every party has the ability to talk to every other party, but you don't want them to use that ability, every time they're doing a computation together, and so sort of during the course of the protocol, the parties determine dynamically who they're going to talk to. It's harder for an adversary to just sort of set up shop in a way that isolates people. So there's this paper that we were looking at back when we were first working on this problem at Lincoln that showed that you can actually do something clever where you get a bunch of parties to elect a quorum of a polylogarithmic number of parties, And you can just send all of your inputs to just that quorum of parties. And if you have a constant number of corruptions with a overwhelming probability, there won't be that many corruptions within that polylogarithmic subset of the number of parties. And you can just have them do the computation, basically. It's a lot more complicated than that, but that's like the general idea. And of course, if you're only having this polylogarithmic subset of the parties do the computation, even if they're all talking to each other, like the locality is still pretty good.
So just
Yep.
The polylog is the degree, or
What?
the polylog is the degree?
Yeah. There's also another paper that came out a few years later, which showed a different strategy for getting a polylog degree of locality, which is using some secret key infrastructure and a bunch of other tools. They were able to have the parties basically decide who to send messages to by each computing, and like together computing like an expander graph, like at each stage of sending a message to someone else. An expander graph is something that is sort of sparse, but is very well connected. And so each party decides during each round who it's going to send a message to next. And it sends it to a polylogarithmic number of additional parties. And then you want each party to get to, you want each message to get to every other party. So after it goes to the next step, then you compute another expander, and then you send it there. And you can show that within a fairly low number of rounds, the messages get to all of the parties within the system. So that's really cool. It turns out that if you want to have just like a broadcast of a message as part of your multi-party computation, so let's say that you are someone with an input to the computation, and you want to just share your secret input to the functionality with everybody. You need what they call in this paper a strong expander. You need something that has you need something where you can't ever, there's no small cut that you can make that can sort of disconnect the graph, because otherwise you're just gonna, with like a lot more care, they're able to show that you're gonna just be able to isolate parties once again. So what's the common theme in all these prior works? Well, one common theme is that we have these malicious adversaries. In some cases, they're what we call static adversaries, which means that we assume that adversaries have sort of chosen which parties to corrupt based on before the protocol has even started and before they know what role everyone is going to play in the protocol. And we have somewhere like over the course of the protocol, the adversaries can choose who to corrupt dynamically based on like who seems important in the execution of the protocol. And in this way, they're able to isolate parties. So a question that we had is, what if we don't have malicious adversaries? What if all we have are just semi-honest or honest but curious, those are both terms from the literature, parties? Think of them as like adversaries who just install some spyware on some of the computers, who are just like looking at the traffic going in and out of the computers, and just trying to like infer what they can about the secrets without trying to like stop anyone from getting information, but they're just trying to learn information that they're not supposed to know. The question is, in this like better model, well not better model, in this model where we're also going to assume there's a static adversary, so the adversary decides who to corrupt before the protocol even starts. And semi-honest, like I said, but you know, the adversary can still corrupt a linear fraction of the parties. Can we get communication locality that's better than polylogarithmic? So we had this idea, we looked at the BGW protocol, and we thought, maybe there's a way to modify this so that in the original protocol, everyone talks to everyone else. Maybe we can modify it so that you don't have to talk to as many other people. So the BGW protocol, It's for Ben Ora, Goldwasser, and Widgerson. The basic idea of how it works is you represent the functionality you're trying to compute as an arithmetic circuit. You can secret share the inputs using something called Shamir secret sharing that I'll explain immediately after this slide. And then the parties together can add their shares and multiply their shares and then reconstruct at the end. So how does Shamir secret sharing work? Let's say you have a secret value 20, and let's say there's like 5 parties in your protocol. What you can do is generate a random polynomial. In this case, I chose a quadratic. And you can evaluate that polynomial at a bunch of points. So f of 1, f of 2, f of 3, etc. If the adversary doesn't control too many of the parties, it's a little hard to see, but I said that I colored in red the adversarial parties there. Maybe adversary controls party 1 and party 3, and so it can learn f of 1 and f of 3. Then you're fine, because there's an infinite number of quadratics that run through just those 2 points. So if you just have that kind of sharing, then the secret that you actually have is totally hidden. But of course, we know that any 3 points uniquely determine a quadratic, and in general, any t plus 1 points uniquely determine a degree t polynomial. So once you have a degree t polynomial, and let's say you have t plus 1 points, you can do Lagrange interpolation, where you have these things called fundamental Lagrange polynomials that look like that. And in order to determine what the polynomial f of x is, you just take a sum of these Lagrange polynomials multiplied by the y values that you know. And from there, you can recover the secret. So once you know how to split up secrets like this in order to do polynomial secret sharing, if you want to add 2 secrets together, all you have to do is add, if you are just one of the parties, all you have to do is just add 2 private shares together. And the reason this works is, like, let's say you have a share which is like f of 1 on a quadratic, and then you have another share, f of 1 on like another quadratic. You add them together, and you get f of 1 on something that, if everyone does it, is still a quadratic. And if both of those quadratics were like random, so they sort of hid the secret to begin with, then the thing that you have after you've added your shares together is still a point on a random quadratic. So that's great. So how do you multiply 2 shares together? Well, you could just multiply your 2 values together. But let's say you have a share on something that is a quadratic. Let's say you have the shares on 2 quadratics. You multiply your shares together and you assume every other party does too. Then you have a share on a new polynomial that has the correct 0, is still sharing the correct secret, but of course you've multiplied 2 polynomials together. So now you have a degree 4 polynomial. And this degree 4 polynomial, the coefficients of it don't look random anymore. So we need a way to both reduce the degree and re-randomize the coefficients of the polynomial. So how do we do that? Oh, I forgot that animation. Okay, so after you've multiplied 2 shares together, maybe you have a share as party I on something we'll call f prod of I, because it's like the product of 2 lower degree things. In order to re-randomize and degree reduce in the same step, all you do is you generate a new random degree t polynomial yourself. And we'll call it gi of x. Then, for each party pj, you send gi of j to each other party pj. The new polynomial that you're going to get out, after you've received your gj of I from all of the other parties who are all doing the same thing, you're going to use Lagrange interpolation again. That Lj of x is the same Lagrange polynomial as on our previous slide, to construct basically implicitly this new polynomial g of x, which is a linear combination of the polynomials that everyone else produced. And crucially, g of 0 from this new polynomial is this linear combination of gj of 0, and gj of 0 in each case is f prod of j. So you're actually taking this Lagrange interpolation of all the points you already had. So then what you get back out is that g of 0 has the same 0 as f prod of 0. And you've actually managed to degree reduce without, and re-randomize and still preserve what your secret is. So what do you do when you have many parties? For this talk, I'm going to say many parties is 9, which obviously isn't really like, why do you care about logarithmic locality if you only have 9 parties? But it's easier to illustrate with 9. So one thing you can do is you need to have a degree high enough that you can multiply and still know what the secret is, and then degree reduce so that you're able to multiply again later. So maybe you have some degree 4 polynomial and you're sharing some secret on that. And every time you want to do a multiplication, you generate your fi of x and you send it out to all the pjs, and that will work fine. But what we noticed when we were looking at the BGW protocol is that you can share things a little bit differently. Instead of having this degree 4 polynomial, maybe just have a degree 1 polynomial, and there are 3, and have, think of f of 1, f of 2, and f of 3, and then share those as if they're secrets too. So have f1 of f1 whose 0 is f of 1, f2 whose 0 is f of 2, and f3 whose 0 is f of 3. Okay, so then how do you multiply? Well, okay, so here I drew secret sharings of 2 different secrets, S1 and S2. If you just multiply your shares together, it turns out that you get basically a quadratic and shares on that quadratic. So we went from lines, lines, lines to quadratics, quadratics, quadratics. One interesting thing to notice is you'll see in the dotted lines that because any 3 points define a quadratic, you can sort of think of wrong way interpolation as something that you can do too. So even though you're actually only looking at the secret sharing of, even though you sort of together share with the 3 parties who are on that solid line with you, are sharing this secret of that first secret sharing. If you look at the 3 parties sort of perpendicular to you instead, they also define a quadratic with a 0. And if you look at the zeros of all 3 of those quadratics, they lie on a degree 2 polynomial that has the same 0 as the degree 2 polynomial that we were initially looking at the first place. So how do we do degree reduction now? Well, we think of that implicit polynomial, and we have the parties, instead of, we have the parties first degree reduce in the opposite direction of the secrets that they actually shared, and get lines out, like I have in this picture. And then we have them do the same thing, but in the opposite direction. And because of just how polynomial interpolation works, we're going to end up, once again, with a linear sharing, 3 linear sharings of linear shares. And notice that in this case, because we had 9 parties, instead of each party having to talk to all 8 other parties, they're in a group of 3 for their first step of degree reduction, and they're in another group of 3 for their second step of degree reduction. So they've only talked to 6 parties instead. And you can see how if you had a really high number of parties, you could extend this. You could have a linear sharing, and then you could have linear sharings on that, and then you could have linear sharings on that, and you could just keep doing this like for a logarithmic, log base 3 number of levels. And in each case, you're only going to have to talk to a constant number of parties on your step in degree reduction. And so we get what we want, which is improved locality, because each party is only talking to a logarithmic number of other parties. So we were really excited about this. We thought, wow, that's so cool. We proved another way to do degree reduction. I wonder why no one's thought of doing this before. It seems like a really obvious thing to do. And we wrote up a paper, and we wrote up a proof of security, and we said, well, if you have a static adversary, then with pretty high probability, if you have sort of a small enough constant fraction of the parties being adversarial, you're not going to be able to work your way up the tree of polynomials to get back to the secret, because they're just going to not be distributed in a way that's going to allow for that. So we thought we were done, and then we found an attack. Okay, so I'm going to pretend we're running degree reduction.
You found the attack after you finished writing the proof of security? Or?
In the course of writing the proof of security, we realized that our proof of security was not complete because there was an attack. So here I'm going to show you degree reduction again, but I'm going to say that we're doing degree reduction on something that hasn't already been multiplied. But that's fine. We should be able to run degree reduction on linear shares of linear shares anyway. It should work. And because you should be able to square things, for example, and then have to run degree reduction on them, and you learn just as much information from this squaring the same value as you would from just having linear shares of that value. So before you've started degree reduction, let's say the adversaries controls the parties who have the shares that I've highlighted in red on the slide. Well, we're a little bit unlucky but we have 4 adversaries, so of course you're gonna be unlucky somehow. The adversary knows these 2 red guys, and 2 points determine a line. And so they're able to learn this point here. But that still seems okay, because you only know 1 point here, so they can't recover the 0 of this long point, of this original sharing. And also, they know this point, because this is also a point on the line that they've now determined the coefficients for. Okay. Now, what do we learn in the next step? Well, the adversary already knew these yellow points. After degree reduction, each party is talking to these parties horizontally that are next to them. And now the adversary can get these points. This green point here and this green point here, because after degree reduction, this is going to be linear. That's the whole point of degree reduction. And once it's linear, it can learn the 0 here and the 0 here. And because it learned those points after degree reduction on the linear thing, and because that has the same 0 as the quadratic had before you did degree reduction, it actually knows the 0 of this quadratic from that it knew that it had before. And once it knows the 0 of this quadratic, it has 3 points on this quadratic, and it can learn this point too, back from the initial sharing. Okay, but now it has this green point on this initial sharing from round 0 before we even started doing degree reduction. And it also has this red point that it just knew because the adversary controlled that point in the first place. So now it has 2 points on a line. It can learn the 0 on the line, and it can learn, just the other point on the line too. So now all of a sudden the adversary has all this information about has all this information about what its shares that it knew before degree reduction, just from the information that it sees during a degree reduction. Whoa. And notice that now that it has learned this point, and it already knew this point, it now knows 2 points on this initial linear sharing before we ran degree reduction. And that's because it has 2 points. Now it can learn the other points, and it can recover the 0. So even though it seemed like we were okay, because we talked to different sets of parties during degree reduction, we actually learned a lot more information than we thought we were going to learn. Okay, so what do we do about that?
Sorry, I have a question.
Yeah.
What was there an intuition for the proof that this turns out to violate, or sort of what was the process of finding this kind of bug?
So we started with just a proof of security that the adversary with high probability, wouldn't learn anything on a fresh sharing. And then we just noticed, actually, in the process of generating these images, that if you looked at what the adversary knew, and you looked at how those shares were related to each other, you could just sort of learn things about previous round from next rounds. I don't think we had any particular intuition.
So,
we just sort of stared
really
at it.
this is a
Yeah.
successful paper for a data visualization.
Oh,
conference,
oh, for sure.
Is what you're saying. I
Yeah.
like it. Yeah.
Yeah. I spent a lot of time on these images in Dixon. But unfortunately, this bug means that it's not really secure. Except for maybe it is, because how often does this happen? If you just have 9 parties, you're kind of screwed, right? With pretty high probability, you're gonna just end up in a bad situation where the parties are gonna be able to learn things from wrong direction polynomials and be able to recover the secret that way. But what happens if you have a whole ton of parties and you have this whole tree of sharings that's of this logarithmic depth? Are you going to be able, is the adversary going to be able to recover the secret using these wrong degree polynomials in that setting? And it seems like on the one hand, maybe not, because the adversary needs to control enough parties in so many different dimensions that there's got to be some dimension where it doesn't have enough parties together to recover something. But on the other hand, there are so many more ways to recover the secret once you get to a higher depth sharing that maybe it's really easy for the adversary to recover. Go ahead.
So how you group the parties,
Mhm.
was that decided in advance, or is that more in the dynamic graph model? Somehow, how do you decide which parties share which, along the tree?
So we just, it's decided in advance. Basically just label each party with, if you have a depth D sharing, label it with a D tuple. And the people it shares with are the people it shares one coordinate of the D tuple with. So
maybe you can make it work if you change your protocol to choose the parties on the fly, in some dynamic way. I don't know. And that your adversary is not adaptive.
So our adversary isn't adaptive.
Yeah.
It's just that the adversary might get lucky. It might just have chosen ahead of time to. We are assuming that our non-adaptive adversary has to choose which parties it corrupts before we've labeled all of the parties. So it's not even that the adversary is choosing who to corrupt in a specific way in order to recover the secret. We just see that their adversary happens to randomly have chosen a number of parties that will let it recover the secret. And we just want to figure out how often that happens. And we stared and stared at this for a long time. We ran a bunch of simulations, and we noticed that the adversary, with the simulations with my like not very good MATLAB code was recovering the secret like 1% of the time with a really high number of n. And we were like, well, is 1% good or is 1% bad? Like maybe 1% is gonna go down even more if we have a higher number of n, but I just like am not a good enough programmer / I don't have enough computing power to like figure that out. But you know, maybe 1% is bad because like it's gonna stay kind of high. Like if it's 1% for like as n just keeps going up, then it's not a secure protocol at all. And so we tried to like come up with some way to analytically figure out how likely it is that the adversary will recover the secret. And we ended up formulating it as sort of a matrix problem, but we don't really know if there are like linear algebra techniques that can be used on it. We don't, or if it's like an interesting matrix problem. We tried asking some people in the math department at our various schools about it. None of them really knew what we were talking about, but I'll tell you how we formulated it as a matrix problem, and maybe one of you has an idea.
A quick question about it too. So is this, if you could solve this matrix problem, would it just be telling you this particular attack success probability is bounded by whatever, or would it be telling you that the scheme sort of is secure up to this, like, is this just a bound that attack, or is it a holistic statement?
So with the matrix problem, what we're able to show is that the adversary can't recover the secret unless it controls a big enough, like a linearly independent submatrix that's sort of big enough to like recover the secret from that. I think it would take another step to show that the adversary's view from what it did see was sufficiently random, but I do think that it could be done. So I think that if we could solve this matrix problem, we probably would be able to prove the protocol secure.
But just that part of it is not fully worked. Gotcha. Okay.
If you did constant depth leveling, would your approach work? Would it be secure?
We did consider that. I don't think that it would, but I don't actually remember what we concluded, so it would be worth looking into. I mean, in that case, you're talking with a logarithmic number of people a constant number of times instead, so maybe it's still logarithmic. That would be cool too.
You also consider
Yeah.
like if you just use not linear but higher degree and say only want to talk to the square root and people or something?
Yeah, so I think it does work with square root n, but we wanted better locality than that. It's possible that you can just raise the degree, but you know, instead of having it be degree 1 and degree 2 things, you know, it's like degree 2 and degree 4 things, or you know, like some higher constant degrees, and maybe it would work in that case. We don't know. But let me tell you about the matrix problem. This is where my slides sort of died. So I'm gonna go to our actual paper. Squiggles, that PDF. Yeah, it's because we had to draw so many squiggles. Okay. So let's say that the secret shares, let's say we're doing like a level 3 sharing instead of a level 2 sharing. And let's say the adversary knows the secret shares of the like S111, S112, like these secret shares that are written in a vector column over here. This matrix on the left is just the matrix of like the coefficients that you get from the Lagrange polynomials. And the vector right next to that matrix is just the random coefficients of the different polynomials that you generated in your initial sharing. So the adversary knows the secrets on the right, which means that it knows information. It knows the information that with these highlighted rows on the left allow it to recover a certain number of coefficients. During a degree reduction step, the adversary also learns information about how a previous round relates to the next round. Which is just a whole bunch of other coefficients. So here's an example of like what happens during a degree reduction round. It has to do some reconstruction based on these, the same Shamir secret sharing degree reduction protocol we said, and it basically gets all of this information about how a degree reduction works. And then now, after one round of degree reduction, maybe it learns some more information about secrets that are on this like differently shaped polynomial after one round of degree reduction based on who it talks to in this round. And then, maybe it learns another set of stuff that it knows after it has done degree reduction, the second step of degree reduction. So basically, what it knows is like some matrix of values that we call Ri from each round of degree reduction, something that allows it to recover some secrets. And then it knows all of this linking information too, of like how each round relates to the next round. So we have this big R matrix of all the stuff that it recovers from each round in degree reduction. And then we have this big linking matrix that has all of the information it knows from each round. It knows just because it knows how rounds are connected to other rounds. And basically, remember that in the initial sharing, we're looking at this whole system of polynomials where just like the first thing in this vector that we're looking at is the actual secret. So if you have this whole thing and then you have like a huge vector of all of the secrets from all of the rounds of degree reduction being the equivalent of this vector here. The secret and then like every coefficient from every polynomial from every round of degree reduction. You basically want to be able to recover just S. And so maybe you don't need to learn all of the coefficients from all of the rounds of degree reduction, but if you have just this huge matrix of all of the R's stacked on top of all of the L's, and then you can find a linearly independent subset of them that includes this column over here, then you can recover S. And so one way to look at this problem is like, how likely is it that you're going to be able to control a linearly independent subset of the rows of this really big matrix and be able to recover the zero that way? We have no idea how to analyze that.
What kind of numbers for n did you get up to in your sort of simulated version?
I want to say we got up to like 1,000. So it's not.
But it's hard, right? Because you got to
Yeah.
look at subsets. So then you're
Yeah.
still looking through a lot of things, even with n equals 1,000.
Yeah. So what we did is we like formulated it as a matrix problem when we threw it into MATLAB, and we were just like, are we able to like find a submatrix that we're able to invert to get S back? And we could sometimes, but not a lot. And that's sort of where we ended. I know that I finished a little bit early, so I'm happy to like talk in more detail about things if anyone has any other questions. But that's basically our idea. I guess I can put my thank you slide up. Oh, no, I can't. Oh, here it is.
All right, any further questions? All right, well, so.
Is there
go
a
ahead.
reason to consider polyglot locality exclusion? Is there something, like, is there a reason why you didn't want to just consider, like, square root and locality? Is there some trivial way of doing things?
So we were just seeing how far we could push locality down. And we knew you could do polylog locality because we read some of the prior works on that. And we just wanted to see if we could push it even lower.
I see.
And you really can't if there's an adaptive adversary.
Yes.
But we thought, maybe with a static adversary you can. And maybe you can. I don't know.
Do you know of any non-trivial lower bounds?
So in terms of lower bounds, we know that if you're not doing broadcast with your protocol, you don't need an expander. And it's the same paper that showed that you do need an expander when you are basically doing broadcast. They showed that there's a way to split up the parties into two groups with like not that many edges between the two groups. And so like there's a cut that's not too big, which makes it not be an expander. And so they show that like you can still do MPC with like pretty good locality and actually polylog locality in that setting. But that's all I know of in terms of lower bounds. Upper bounds, other.
All right, so we'll be back here tomorrow for talks, and tonight